So welcome back, everybody. So far, some more to come, but I think we will continue with our Friday session. And yeah, we had these headlines about advanced techniques. We want to have some cross-linking topics, and even now it's a pleasure to introduce Victor Pandolfelli with his talk. And I mean, I do not have to introduce you so much in our field. Maybe for the young people here as well. You're really someone very, very dedicated for many, many years in the field of refractories, always in a fundamental way, transferring to industrial application as well. And I'm very glad that you had this view into the future, but even with an old title, The New Stone Age, and you bring something.
Let us see.
Let us see. I'm very glad that you have here, and I will start your presentation. You
Okay.
need a this is
Yep.
you need some.
Thank you very much.
And all right.
Okay. Welcome back. Not all of us. Oh, is it okay? The sound?
Yes.
Okay.
Or you can, if you stay at the desk,
Okay.
it's fine.
Yeah.
Just if you walk around.
Okay. It's a pleasure to be here. When we were thinking about fire in 2003, Michel Rigaud invited myself, Archai, Magnesita, because it was not the same industry at that time. And he presented the idea of fire. And at first we said, it's a good idea, but how to work out, how to prepare everything. And fortunately, based on his vision and efforts, in 2005, we had the first official meeting of fire. And now, 20 years later, we are commemorating our anniversary. And perhaps some of you didn't even have born at that time. And fortunately, we have great minds behind the fire nowadays. And we are very happy that the fire is going to continue. Okay. Perhaps you don't know very much about the work that we carry out in Brazil. Let me just continue here. Okay. And we work very closely to industries. About 70% of our budget comes from industry, 30% from governmental and funding institutions. And nowadays, most of our students either go to the industry, fewer of them on academy, and most of them, they are going to startups and spin-offs of our department out of their research. And they are the third largest founding people of my group. That means that these startups are not just leaving our department, but also are sponsoring because they had good experience and now they want to propagate that to the new generation. Okay. Well, the title of the presentation, it's very tricky. And if you move to the title again, The New Stone Age, of course, that everybody's familiar with this picture, but not everybody knows because the Stone Age ended. And it didn't end due to the lack of stones. We still have stones nowadays. It ended because it was time to think about how we live. And this is the situation that we are facing nowadays. Né? Sometimes we think, oh, everybody's changing. It's like, oh, the needs changed. Then things need to change. Then we moved from the stone arrow to the metal one and now to the digital arrow. Then we are now facing the new digital arrow era. And it's changing so much that even our vocabulary has changed. Now, A, by artificial intelligence, B, big data, C, cloud computing, D, data mining, E, environment, and you can follow. All started based on computational simulation. I'm not saying that it has ended. We have seen yesterday that there are many, many works that still have been done on simulation. And of course, it came to stay, not to leave, because it's a very important tool. I will base my presentation in results of my group, things that we have been carrying out at the moment, not in the past. It's not a historical view of our group. And one of the things that we have been using simulation, it's to study the drying of the castables. Huh? Uh, uh, the advantage of the techniques that you have nowadays, it's not just involving simulation, but the new tools that you have to analyze the materials. For example, in this case, we have been using neutron tomography to see the drying inside the castables. Huh? And for example, what you see now, of course, in very high speed, it's a castable in your left with polypropylene fibers, the second without fibers, with a cellulose fibers that it's something that we have been working deeply because it's a natural fiber, very cheap, and polyethylene fiber. And sometimes we think, but why we're studying fibers? It's so well known about fibers. Believe it or not, so far, people don't even know how fibers work. You'll say, why not? It's just to melt it. But look at, if you compare, for example, PP polyethylene fibers, they have different melting point. The polyethylene fibers melts around 95 centigrades, and the PP around 150. And based on the studies that we have done for quite a long time on drying of castables, we never had explosion using PP fibers. With the all others, we had explosion. And the melting temperature is not the lowest. Then it means that there are mechanisms that are working together to improve the drying. Then sometimes people ask me, well, you have studied so many things, of course, based in my age, in refractories. What else it's necessary to study? I get puzzled because I don't know whether I started, because there are so many things to be understood and so many technologies that we want to generate that for us is just the beginning. But this sort of technique allowed us to simulate them based in what we had seen, because sometimes people think that when you use Newton tomography, you see the drawing. You don't see anything. You get numbers. And just to have that previous slide, it took 6 months. This is the reason when we see that the James Webb telescope, they got an image. Uh, and you think, well, it's just like a telescope. You go there and you see, and it's there. No, they get numbers. Based on that, you need to work very hard on that numbers to get an image. And this is the purpose of our talk today, because sometimes we think that, oh, machine learning, everything, just like that. Not like that. Okay? Don't forget the saying, garbage in, garbage out. Huh? If you don't get rightly, you get nice images, but no sense. This is for the first time in 125 years of the Journal American Serum Society, this image got the front cover of the issue last year. We are very proud, not just for our achievement, but for fire achievement, because all the results that we're going to show here, they are related to fire projects. And perhaps if it was not fire, we would be not that big. But what is important in this image, for the first time, we could see that we detected what is called water clogging in a material. You see this darker region here. This is representing not water vapor, but vapor that has liquefied inside the castable. This is the reason that sometimes when you are drying the castables and you have the wick holes in your steel plate that contains the refractory, the liquefied water can reach length about 1 meter, leaving the drying castable. But you say, well, it was vapor. What happened? Huh? Uh, the liquefied one. And this is a major difficult for us to study, because suppose that we are measuring the permeability of your castable. You say, well, I get rid of the free water, I got rid of the binder and all the phases that were linked to that. But suddenly, and close to the cold phase, you have liquefied water that it's inhibiting the vapor release. Then your permeability is starting to decrease again. And you just realize that if you're hitting your castable and one side, if you hit your castable from all sides, you don't see that. Then you are out of reality. Okay, but why you did that? Because we want to adapt our models. If you don't see, you can have any models that you think that are fitting. But when you have what is going on with your models, you could adjust the models. Sometimes people think that, well, to simulate drying, it might not be that difficult. You have 30 different variables involved, And most of them, we don't even know how to measure it. Then which model are you going to use? How complex? If you have a model, you need to insert values. Which values are you going to insert if you don't know even how to measure it? Then you need to simplify and see with models that you can evaluate the properties, you can do the job. And this is a hard work. Of course, everything is simple when you see the final result and it works. SpaceX, just send a rocket and huh? But I was telling Hong yesterday, some of the SpaceX projects, they failed because the launch pad, that it's a concrete, exploded. Why? Because low probability, drying. And imagine, take the hypersonic velocity that we have seen today with John and hit up your castable beneath your rocket. It exploded and all the fragments of the base damaged, and you spent millions of dollars, let us say, to realize that refactors is important. Well, when you get a model, then you start to get the benefits of the model. This is, it might look complex, but if you focus on the black line, you see the internal pressure that you get with the cast inside the castable as you decide what is the heating rate that we're going to use, how long it's your dwell time, at which temperature, how many dwells are going to insert in your material. Then you start to engineer the heating curve. Right? Why? Because in the end, you want a short heating with safe heat. Because we have seen yesterday by Hong's presentation what happens if it exploded. Not just that, using fluid mechanics as well, we are designing the whipping holes. Perhaps not most of you know what it's the whipping holes. When you have the working layer, the permanent layer, the insulating layer, we have a fourth layer that it's the steel metal. And the vapor needs to escape, or the liquefied water. Then you need to place holes in the steel shell. But so far, this distribution of holes has been done just based on the structural effect on the ladle, never considering the drying. Then we are trying to cope these two things, to place the holes in the steel shell, of course, not affecting the mechanical structure, but trying to better speed drying faster the whole container. We are using simulation not just for drying, also for bubbles. Of course, that during this school, you are going to see the same problems, perhaps trying to be solved by different ways. This is quite rich. Well, we don't have just a way to solve a problem. And why we're doing simulation here? Because we have, during the the process or in the label, we have at the bottom, we have the porous plug, that it's where argon is injected besides the ladle. And the main purpose of this gas is to generate bubbles to trap the inclusions. Inclusions that could come out of the refractory due to the corrosion or oxidation of the metal and things that might be in the metal. And the final stage is to take this inclusion to the slag. But we studied each part of this process. The first one that we studied was about what types of refractory we could produce the purging plug. And nowadays, most of the refractories that they are producing is based on alumina or spinel, the alumina magnesia spinel. Okay, but when you compare, if you see that line, green line at the bottom, this is the size of the bubble that would like to have to better trap the inclusion. And when you consider the wetting angle of the alumina and magnesia by the steel, you realize that the bubble generated are far above the one that we would like to have. But why that? Why are they using alumina, magnesium, and not silicon carbide? That it's quite close. Due to the infiltration, because you have the ferrostatic pressure, you have also the corrosion of the steel. And when it infiltrates in the porous plug, you need to clean that afterwards. Otherwise, you cannot blow any gas anymore. And how do you solve that? With a torch. Then imagine trying to remove that ladle, that layer with a torch. You destroy everything. Then you would like to have something close to silicon carbide, but that couldn't be wet by the metal. Then why not to have alumina, for example, or spinel piece, where the size of the pores would be very small in order to generate small bubbles. Yes, uh, Professor Nesiri said, for example, that 3D printing would be a good idea to have a porous ceramics with a narrow or pore size distribution. If you read the Junior European Ceramic Society next issue, you are going to read our paper about de-alloying ceramics. It means if you form the spinel and just afterwards you disintegrate the spinel. And what we had got with that, it's a pearl size with a very narrow range of 0.7 micrometer. And you say, but is it stable at high temperature? Well, it was first sintered, and that one below, it was left in the furnace for many hours at 1500 centigrade, and we didn't have the change of the pore size. And you don't need to have the full piece of the purging plug made of this material. But let us say the top layer, because in that case, you are going to reduce the infiltration and have the size of the bubble that you wish. But what is the uh, objective of this? It's to trap the inclusions. Then we have the whole study, how to trap this inclusion. Because look at what the customer wishes at the end is not to buy a refractory. He wants to buy clean metal. Then, sometimes when our partners, we're not saying that we sell refractory. We sell solutions. Right? Although, and the refractory is part of the solution. Look at our objective. It's not to, let us say, produce a refractory to have a clean metal. It's a container, but it's what the customer wants. Then you need also to think if your refractory is corroded, how to remove that sort of things. It's like recycling. You produce something and you want to now to get rid of that, produce something useful. Huh? And we have studied, and Luis Otávio is here, Luis Otávio is there. Né? He did this part of the job, or the whole job, actually. And we had as a partner of this part of the cleaning inclusions, partnership with Stat Steel Netherlands. But we are not just thinking about removing the inclusions. We're also thinking about the bubbles at the slag. It means we are slag foaming. And why are we going to slag foaming? To have a nice slag? No, it's not just for that. It could be, but it's not the main purpose. The main purpose of the slag foaming is to insulate the metal and avoid oxidation. Also to protect the refractory that it's lining the furnace. And it's quite interesting because you generate a bubble to trap the inclusion. Now, at the top, you add particles to stabilize the foam. You see, it's the same technique with two purposes. And we developed this whole work, and the first customer that appeared, he asked, I have a problem of foaming too much. I want to defoam it. Well, if you know how to foam, you should know how to defoam, right? Just to apply the inverse process. But this is our future. We need to use the basic science to solve problems. We have a motto for our group, user-inspired basic research. We don't do basic research just because we want to publish. We want to have what is your problem. Where do you want for the future? Then we need to study and use the basic science trying to solve that problem. But computational simulation, it was just part of the history. When Thorsten asked me, he said to talk about going further. Then I have this picture that I don't know whether you're familiar about the Janus god. Janus god is a Roman god, and Janus, it generates the name January. Because if you take the photo of Janus, the statue of Janus, uh, it has two faces, one looking the past and the other looking the future. But realize that this channel does not suit anymore because he's looking the past or he's looking the future with the same eyes that it's looking the past. We need another Janus. We need the Janus of the new brave world that looks the past, but looks the future with a different eyes. And the other motto that you have that is looking the future, not neglecting the past. We need of the history of the past, but we need to see the new challenges. This is the name of our project, actual project with FAIR, Janus Project, based on that image. And where I would like to get nowadays, everybody's talking about the data mining, machine learning, artificial intelligence, ta 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 ta. You have different names. Uh, but what it's about and what it's the purpose? Well, what you want in the end is to generate materials or process either top down or bottom up. If it means if you are bottom up, you are playing with atoms and you are engineering that to get a material in the end. The other way around is you have the material and you start to decompose that material and go towards the ab initio, the beginning of everything. For example, it's very useful for electronic ceramics because you need quantum mechanics that to put the atoms in the right position. Or using molecular dynamics, we are quite familiar with finite element method, but there is another one intermediate that it's very important, that it's called phase field, that allow us to study the interfaces and the grain structure. We're trying to deal with that. Then I'm going to give some examples, not yet of machine learning. At the end of the presentation, it's going to be rich in machine learning. But what we have been doing using simulation plus data mining. Okay? We have heard yesterday by the talk of Jack now about the importance of data mining, because in the steel plants, mainly, what you have mostly is data. And unfortunately, most of these data are not being useful. Uh, they're there. They are measured, but don't know what to do with them. And we're going to see that it's not that easy. It's not just because you have quite a lot of the data that you can do machine learning. I just would like to point out the importance of the data. Uh, in the Second World War, they realized that most of the airplanes that landed, they It's not just one plane like that. Fortunately, otherwise it will not come back. But most of the holes that they have in the structure were that red dots. Then they had data. Good. What to do with the data? It's telling to reinforce our planes in that areas. Logical. Well, they did that, but they realized that the percentage of planes that are coming back was the same. Then someone said, well, it means that the planes that didn't come back had holes in another area. Otherwise, they would come back. You see how tricky our data? It's not just because you have data that you have the solution. Perhaps you need to go in another direction to solve. One example, I'm worried about the time. I like to talk. uh, uh, if you're producing, for example, complex ceramics, one of the problems, sustainability problems that you have nowadays is with chromium oxide, right? Because chromium plus 6 is carcinogenic and it's a big problem. Then we would like to mimic the microstructure of magnesium chromium, but not using chromium. And you see that the structure of the magnesium chromium is very complex, and you see well-defined cracks there that gives plasticity or elasticity or flexibility to your material. It's very important for thermal shock resistance, as you have seen yesterday by Mark's talk. Then we selected, based on that, uh, doing the simulations, we selected 154 distinct systems that could closely describe the magnesium chrome system, but without chrome. Based in many descriptors, but this is the 5 most important. And based on that, we have selected 4 of them. And we produced the first one in the lab, electric fusing in the lab, and we generated this sort of microstructure that it's quite unique for refractories, and we started to study that microstructure and realized that it was a 3D network microstructure. We put our sample in chloric acid, and it removed the MgO after 7 days, and we could find out that this spinel structure, like dendrites, it was a 3D. Then John was talking this morning about the woven microstructure and what you need to do to get in. I say, look at, that's it, without any further cost. Okay? Then imagine if you are a crack and you want to cross this area. You are going to have quite a lot of difficulties. Right? This is fracture energy. But when we try to produce the same microstructure in the industry, we replied it was the same. And up to this moment, the trials that we are doing in the industry, they are showing that all the properties of this novel aggregate are better than the magnesium chromium, and the corrosion is the same. Then we are getting good performance without chromium, but we want to go further. This is what we have been doing nowadays with our partner in this project, RHI Magnesita. Okay, but this is data mining. This is not machine learning. No? Then we, in parallel, are doing that for refractories. And the first thing that we need to do is to select your model. You have quite a lot of the data. Okay? For example, if you get materials for the steel industry, they give you, for example, 4 different datas for the process, not just the steel, right? But the furnace, sea condition, everything, partial pressure, everything that you want, with at least 5,000 runs. Then you have a matrix of 5,000 by 40. You say, it's the dream of data. But when you start to analyze this data, you start to see that they were not collected evenly. Someone, let us say, in one result put a trace. The other, it's blank. The other put a knot. What does it mean? Because the guy that did the note in there didn't even know the one that begin 5,000 runs before. Okay? Then how to sort out that? That is not just a matter of having data. You need to do the cleansing of the data. You need to select and prepare your data. This takes 70% of the time of your machine learning process. It's not just to have the data. This is just for the situation that you have data. Imagine if you don't have data. You need to create them. Okay? We faced a quite interesting challenge. One, the industry came to us and said, you are doing machine learning for a fact. We are learning with the time. Okay, I have the data, but I want to give the same set of the data for your team, and I'm going to hire a team that specializes in data mining and machine learning. It's a difficult job. Okay. The difference was we know a bit of refractories. They know nothing about refractories, but they are familiar with all the computing and things like that to choose the model, everything. Okay, let us go. But they work for any sort of industry that you couldn't imagine. Right? Then what it was the main conclusion for them said the main importance for refractories is temperature. Wow! Wow! Come again. I didn't understand. It's a novelty for me. What is most important? Temperature. Oh, yeah. It means that I paid, that I gave you my clock for you tell me the hour. Yes. And this is very important because most of the time, what the top level of the industry thinks is that why we are going to generate your own group of machine learning. We hire, and good idea, boss. Good idea, boss. We send the money. Yeah. But do they know what they are doing? When they have these gaps, do they know whether it's valid or not, that data? Do you know how to eliminate one of the columns that could be not important? Take care. Take care. Because otherwise you are paying to have the same answer. Temperature is very important for refractors. Well, fortunately, you got the job. But selecting the model, it's not that easy. And sometimes we think that we need to select the uh, best model, the updated model. It's not like that. Huh? Actually, what you need to do is not to find the best model, but finding the one that answers your question. Okay? I have many more things to tell, but I'm looking at the time. Uh, when you consider about metal and machine learning, you realize, no, I'm going to take a picture. Let me pause this. And when you think about metals, they are well in front of us. Okay? Not because they know much more about the computing techniques, because they have data, they have a molten metal. It's, you know, right? Uh, it's a more constant process, whereas in our case, it's much more complicated. There's this company from Finland that they grow from the beginning to the end of the process just by computing. They can build up a factory just by computing, but no experience about refactories at all. And they use, of course, the same techniques that I'm talking about. DFT, density functional theory, molecular dynamics, the computing, Abacus, ANSYS, everything, because they go to micro scale to big scale. Okay? Then what is important nowadays? It's what is called integrated computational materials engineering. This is what we should look at. The first job that we did some 2 years ago on machine learning applied to a steel company. Actually, we are hired by a refractory company, and Red Lab is one of the startups generated in our lab. It was to work out what is the quantity of mass that we should have for a tap hole. The tap hole is the valve, let us say, in the blast furnace that helps to control when you are going to have finished your run. Huh? In comparison, it's like the valve in our hearts. If it does not work well, the system goes crazy. Then imagine the steel ladle and the whole process ready to receive the metal. But the tap hole mass it's not working properly. Either releases the pig iron early or later. And the torpedo ladle is waiting the metal there for the other stations for treatment. Okay, metal. No, metal it's not ready. Then it complicates everything. Actually, it was not this machine learning, but when I worked with step hole, it was the most difficult subject that I have ever worked with. You don't imagine the complexity of a taple hole mix. Aluminum silicon carbide, well, we have half of the periodic table there. And they know why, but it works. Then keep like that. Okay? Because you have injection, drilling, wearing, corrosion, oxidation. Paul, tell us about this nightmare later on. No? And they would like to have a more stable process. And for that, you need to know what is the quantity of mass that you need to inject. Then we develop based on the data. As I said, you have quite a lot of data. 70% of the time you are selecting these data and work with them. And after you are familiar with the model that you are going to work, right? For example, neural network, something like that, you try to teach your software how to work with data that you don't know. The software does not know. First, you train the software with the data that you have, but select part of them, and when you think that it's trained, you give a challenge, a new challenge to the software, and say, then solve that. And he's try to predict what is the amount of the math, and you need to test. Okay? And if you are going to say that you are going to have 100% of reproducibility, perhaps you are not aware what is going on. Because if you are getting something close to 60 to 80%, you are in good hands. Because the number of variables that you have, sometimes the software can perhaps there were not enough data for a good prediction. Then we developed the software, and it has been used by the industry with success so far. It's almost at the end. Could I have some spare minutes? I started 11, let us say 11:30, roughly. Roughly. Uh, 10 minutes, it's more than enough. Okay. I'm going to speed up, okay? Because now it's the story that what happens when you are not working with the steel plant and don't have the data. You need to generate the data. And what is our focus now? We're working, one of the projects is with transient liquids. It means you have, yesterday we heard about the liquid phase sintering by Thorsten. Then you would like to see to sinter at the low temperature but at high temperature, you don't want to have glass anymore. Then this is a transient liquid. This is what we see in this system. If you take, for example, the red line, you see that around 700 centigrade, it starts to increase the elastic modulus. And after the first run, if you run again, that it's the yellow line, you don't see the liquid anymore. This is very good because you can save energy, you can save time, and you still have a very suitable refractory. Then we started to create models that could simulate what we have seen. And we were confident about this sort of models. Then, after that, said, okay, we are confident about the model. How about now to select one system that we suppose that by our simulation that it was a liquid transient, but if you go to the phase diagram, you don't see liquid. Then we tested this quaternary system, right, that you don't see liquid phase there. This is an image just generated for you to see that you generate in blue the liquid, and when you increase the temperature, the liquid disappear. And not just like that. You could see different phases that are forming if it runs properly. I think that it got stuck. Yeah, no, it's running. But look at the liquid there. You start forming, and the different phases that we have, not just the liquid, but a different one. And when you perform it, the castable to sift, we saw the spinel formation of this zinc oxide and aluminum, the liquid formation, no magnesium aluminum spinel formation. Then one spinel here, no spinel here, and a liquid in between. And if you run twice, you don't see the liquid. Why you know all of that? Because if you substitute the calcium aluminate by hydratable alumina, you see the spinel formation, you don't see the drop, and you see the aluminum magnesia spinel formation here. What we are doing now that we are getting more confident, we are working with more complex system, and the big challenge that you have today is to use our capabilities. We don't know whether it's going to be enough to analyze the in situ corrosion, like things like that you could, as the slag or the metal advances, you see what is going on the surface of each aggregates and in the matrix. Now my final slide. Is it okay for you now? Better. Perhaps you think I'm not quite confident that this is the future. And when we are not confident, we need to ask help to someone with more experience. This is an experience that has been done in Switzerland and started next year, where they have a confessional booth where they taught the software in all the Christian religion's fundamentals. And the different, the pure Christian, Catholicism, Orthodox, everything. And they taught by machine learning, and the software can speak in 100 different languages. And it was more important, you can talk directly with the man. Okay? To have your device, the language that you want, and all the doctrines that you are used to. 70% of the people that use the system, they said that they had a spiritual experience. Let us see. Thank you very much. I just finalized. Thank you, Murilo, Otávio, and Julie for all the help. Sorry for that.
Oh, I mean, it was a pleasure to follow. Of course, it's always good to follow your outline. But I think a bit out of questions, so out of time for questions, since we have another talk this morning. No, it's right. I think, yeah, we continue for, I think there's a bit more to come now because